We are coming at you from West Virginia. Eventually, I will come at you from West Virginia. But what I am definitely going to do right now is give you Joke of the Day, because I know you love Joke of the Day, so let's get to it. It's my favorite part of the day, too. So what do you call a pile of kittens? You know, baby cats, kittens. What do you call a pile of kittens? A meowton. Joke of the Day is the best part of the day, isn't it? I know it is. All right, well, let's climb our way up to using the point plotting method to graph nonlinear functions. Now, we looked before at using that point plotting method in order to graph lines, but you can use the point plotting method to graph any type of equation, any type of function in the 2D coordinate plane. But before we get there, we need to recall that any of our graphs, the graph of an equation in two variables, meaning it typically an x and a y, it doesn't have to be an x and a y, but that's typically what it is. When you have two variables and you've created that 2D coordinate plane, because we've talked about how if you have an x variable, you have one line, and we've looked at the solutions on that line. When you have a second variable, you've got another line. How are you going to put the two together? Bam, like that. That's how the 2D coordinate plane is created. So when you have two variables and you have this 2D coordinate plane, and you're going to graph your equation in that 2D coordinate plane, critically, crazy, unbelievably important that you understand that that graph is the set of all points whose coordinates satisfy the equation. So in other words, when you put that graph on this 2D coordinate plane, every point on the graph is a solution to the equation, because the coordinates for every one of those points, if you take one of the points on the graph and you get its x coordinate and you get its y coordinate and you put those coordinates back into the equation, it will create truth. Anything off of the graph will not create truth. So let's take a look at a couple examples here, and I'll re-illustrate this idea of those being solutions once we get through the examples. So recall, your point plotting method says, I'm going to create this chart, and I'm just going to pick some values for x. I'm going to throw them into that function everywhere I see an x. I'm going to follow those order of operations. It's going to spit a y value out, and that will create an ordered pair, because I'll have an x coordinate, I'll have a y coordinate, and that creates an ordered pair. Remember, it's called an ordered pair because order matters tremendously. If you mix up your x and your y, you have a completely different point on the 2D coordinate plane. So order matters, and that's why it's called an ordered pair. But this ordered pair represents the relationship that has been established by that equation. So this is a relation. So the directions of the example say we're going to graph it, and typically you can pick anything you want for your x. But these directions say we're going to start with a -3, we're going to end with a 3, and we're going to select integers. Integers leaves out what types of numbers? Yes, leaves out fractions and decimals. So we're going to start with a -3, we're going to end with a +3, we're only going to include integers, so that would be a -2, -1, 0, 1, and 2. Now, what we're going to do with those numbers is we're going to plug them into this function right here everywhere we see an x. So here's the function. I'm going to take that -3, I'm going to plug it right in there where I see that x, and then I'm going to follow order of operations, which PEMDAS says do this exponent before we do that addition. So a -3 times a -3 is +9. +9 times -3 is a -27. -27 plus 4 is going to give me a -23. And so the relationship that has been established by that equation says when the x is a -3, the y comes out as a -23. And that's what this ordered pair is communicating to us. This is the relationship that has been established. When x is a -3, y is a -23. So let's test it out with the -2. That says let's put a -2 where we see an x right here, and we're going to follow that order of operations, which once again says do the exponents first. So a -2 times a -2 is +4. +4 times -2 is -8. -8 plus 4 is a -4. So once again, the relationship that's been established by this equation says in this case, when x is a -2, y comes out as a -4. And again, that relationship is being communicated by the order in that ordered pair. So let's try it out with a -1. Once again, following the order of operations, exponents first. -1 times -1 is +1. +1 times -1 is -1. That -1 plus 4 is a positive 3. So again, the relationship established here is telling me when x is a -1, y is a 3. The order matters tremendously. So let's test it out with a 0. Once again, order of operations, do the exponents first. 0 to the third power is 0, plus 4 is 4. So that relationship is now when the x is a 0, the y comes out as a 4. So let's keep going with these positive integers, and you may be thinking, oh, well, all I have to do is change the sign on this, so all I have to do is change the sign on this. Well, 1 to the third power is 1, 1 plus 4 is 5. Whoa, no, don't just change that sign. We need to follow that order of operations to see what comes out. Now let's test it with the 2. So, exponents first, 2 to the third power, 2 times 2 is 4, 4 times 2 is 8, 8 plus 4 is 12. So the relationship established here says now when x is a 2, y comes out to be a 12. And let's finish that up with our 3. 3 to the third, 3 times 3 is 9, 9 times 3 is 27, 27 plus 4 is a 31. So this relationship establishes now when x is a 3, y is a 31. With all these ordered pairs, you know you can put those on the 2D coordinate plane. So we're going to graph these and see what happens, what our picture will look like. When x is a -3, y is a -23. Well, here's x is -3. Actually, y being a -23 is going to be way, way down here somewhere. I'm out of room on my graph. So I'm going to pick up this -2, -4. So when x is a -2, y will be a -4, and that's going to sit right down here. Okay, now let's grab our -1, +3. So when x is a -1, y is a +3, sitting right here. When x is a 0, y is a 4, sitting right here. When x is a 1, y is a 5, that sits right here. When x is a 2, y is a 12. 2, 4, 6, 8, 10, 11, 12. It's going to sit right up here. And 3, 31 is again going to be off the graph. Now when I connect these, notice that what happens here is we get a funny little curve. And this should not be perfectly vertical. It's going to kind of angle out this way. This is a plug for graph paper and a ruler. Well, not so much ruler, but graph paper most definitely. Because the curve, quite frankly, should look a little more like this. I just don't have a real good graph there. But you can see here that it's definitely not a line. But we do have a graph that was put together by the point plotting method. It's a tried and true method. If you forget all those other shortcuts with your x and y intercepts and slope intercept, now granted that would not work here because it's not a line. It's not a straight line. So whenever you have nonlinear functions, point plotting is one of the best ways to get there. But I do want to go back over this again. The graph of this equation, so the pink right here, is the set of all the points whose coordinates satisfy the equation. Clearly, if I pick this point out right here, that's 1, 5. If I put 1, 5 in here, then put a 5 right here where the y is, put a 1 right here. Well, we just figured out that when we put a 1 in here, we did come up with a 5. So these coordinates will satisfy that equation. If we pick this point right back here, which is -2, 4, and we put a -4 in here and put a -2 in here, when we put that -2 in there, we did discover, oh, we did come up with a -4. So every single point on this graph will create truth, where the left and the right sides come up to be the same. Not just these points that I've got dotted here, but every point in between. If we could figure out the coordinates for, say, for instance, this point right here, if we could figure out those coordinates, we'd put its x-coordinate here, we'd put its y-coordinate here, it would still create truth. Meaning that when I do the order of operations over here and I cube it and then add 4, I will get what I got over there. Everything on this curve creates truth. Everything off of the curve, everything over here and everything over here will not create truth. Let's test it out. Let's pick the 4, 1. So if I put a 4 in here, 4 to the third power is 64. 64 plus 4 is 68. We said we should come up with a 1. See, that does not create truth. And the same thing's going to happen over here. Anything you pick over here and put in there will not create truth. So it's very important that you understand this statement right here. Anything on the graph creates truth. Anything off the graph does not create truth. So let's take one more example of this point plotting method. Take a look here. This is another nonlinear feels kind of linear, but notice there's absolute value around that x. That's going to make a huge difference in what happens. So point plotting again says pick some values for x. Our direction says let's limit ourselves to a -3, -2, -1, 0, 1, 2, and 3 because we want integers between -3 and +3. But that point plotting method says take these values, put it right here where we see that x. So we're going to put it right in here, and we're going to follow those order of operations. Now here it's kind of weird. How are we going to follow order of operations? Well, absolute value kind of acts like a parentheses. So we'll do absolute value first, then we'll multiply by that -3. Well, the absolute value of -3 is 3. -3 times 3 is -9. -9 plus 9 is 0. So the relationship that has been established here says this time when x is a -3, y comes up as to be a 0. Because remember, in the previous relationship, when x was a -3, y came up to be a -23. Totally different relationships that are being established here, so it's creating different results. And again, this order matters tremendously. There's a huge difference between a -3, 0 and a 0, -3. They are two different points on this 2D coordinate plane. So let's test out that -2, put it right here where we see that x. And once again, let's do that absolute value first. Absolute value of -2 is 2. -3 times 2 is -6. -6 plus 9 is 3. So because of this relationship that's been established, it says this time when x is a -2, y comes up as a 3. Again, different than what we had previously, because previously when x was a -2, y come up to be a -4, not a +3. So, different relationship is causing different answers. Now let's test out our -1. Put that in the absolute value. Do it first. The absolute value of -1 is 1. -3 times 1 is -3. -3 plus 9 is 6. So now the relationship up here says when x is a -1, y is a +6. Yet again, totally different than what we saw here. This time when x was a -1, y came up to be a 3. So clearly you can see all these relationships are going to be different because this is a different relationship established here. So let's continue it on down and put that 0 in there. And so absolute value is 0 is 0. 0 times anything is 0. And that 0 plus 9 is 9. So this relationship says this time when x is 0, y is 9. And now let's continue on with our positive integers. Put that +1 in there. Well, the absolute value of 1 is 1. 1 times -3 is -3. -3 plus 9 is 6. So now when x is 1, y is 6. Well, that's interesting because when x was a -1, y was 6. Well, let's try out our 2. Absolute value of 2 is 2. 2 times -3 is -6. -6 plus 9 is 3. So the relationship established here says when x is 2, y is 3. Well, that's interesting. When x was a -2, y was 3. Are you noticing something? Aha. Yeah, we increase by 3, increase by 3, increase by 3. Whoa, decrease by 3, decrease by 3. What do you think this is going to be? It's probably going to be a 0. Well, let's check. Let's put our +3 in there for the absolute value. Absolute value 3 is 3. That 3 times -3 is -9. -9 plus 9, yep, it's a 0, just like we expected. So once again, the relationship established here says when x is 3, y is a 0. So now we can put these points on our 2D coordinate plane. -3, 0 sits here. Remember I said order matters, because if we flip that around, 0, 3 would sit here. So these are called ordered pairs because order matters. Now -2, 3 sits right here. And -1, 6, 3, 4, 5, 6 sits here. And 0, 9, 2, 4, 6, 8, 0, 9 sits here. 1, 6 sits here. 2, 3 sits here. And 3, 0 sits here. And we connect them. Now, why am I not putting a curve up there? A lot of other times I put a curve. The previous graph was a nice little curve. I'm not putting a curve because of this absolute value that's here. Absolute value always has a V shape. It's either V like this or V like this. This V's down, opens down because of the negative coefficient out here, which is not something you need to worry about right now. The bottom line, the point of this video, this lesson, is just to get us familiar with the point plotting method, which says pick some values for x, throw them into your function where the x is. It'll spit y values out based on the order of operations that you're doing. That will create an ordered pair. Order matters. That's why it's called an ordered pair. You can put those on the graph, and then you have your graph. Remembering what is on this graph, those points, even if I could figure out the coordinates for this one right here, whatever that x value is, I'd put it in there. Whatever that y value is, I'd put it in there. It would create truth. Once I took the absolute value of that x and multiplied it by a -3 and added 9, I would get whatever that y coordinate is. Everything on the graph creates truth. Everything off the graph over here, off the graph over here, and off the graph over here does not create truth. For instance, try 0, 0. Put a 0 right in here. Put a 0 right in here. Well, we did 0 right here. Absolute value of 0 is 0 times that is nothing, plus 9 is 9. See? We should get a 9 there. So 0, 0 does not create truth. So hopefully this helps you to understand the beauty of the point plotting method and how valuable the point plotting method is for graphing, particularly your nonlinear functions, because you don't have a lot of shortcuts with your nonlinears. With your linear functions, you do have shortcuts like your x and y intercepts. You've got your slope and your y-intercept. But hey, if you forget that stuff, point plotting always works. And really, to drive home this point right here, everything on the graph is a solution because those coordinates will satisfy the equation. Everything off the graph is not a solution because their coordinates will not satisfy the equation and create truth. It's all about truth in math. I hope that helps. Have a great day.